All right, so here's the second part. Told you what the formula was.
Yeah.
Told you about Sierpinski.
Okay.
Here's what they think is the smallest number, but they don't know for sure if this is the smallest one.
Okay.
Which is kind of surprising because not knowing if something is the smallest, you would think is an easier problem because what do you have to do to find out if it's the smallest?
Well, find one that's smaller.
Yeah, or check all the odd numbers below this.
Yeah.
But it turns out it's not so easy to do, and there's still 4 numbers that they're checking, even now, like
Are they
right now,
like
today.
huge numbers?
Well, no, they're less
They're
than
less than that.
they're less than 78,557. But what do you have to do to check?
But they have to check all the powers of 2.
Right, and so how do you cross a number off the list?
If you test it, if you know that this will never be a prime number, if you find it.
Yeah, if you find a prime number.
So you'd have to find like sort of a pattern in the powers of 2. So you could cross off a lot of numbers because you can't test them all.
Well, yeah, it's tricky, right? You might have to test a lot of numbers. But before we get into that sort of idea, and maybe we can test 3, for example, or 5 when we go upstairs to the computer.
Okay.
But how do you think someone would even think about this? Like, and this was 1968, so they weren't running upstairs to their study to play around with Mathematica.
Well, they might have like found patterns in the powers of 2 that would let them cross off numbers even like without testing them.
Oh, okay.
You would test other numbers and
Maybe
find
there were
a relationship.
Yeah, maybe there were patterns in the powers of 2, for example. Yeah, good idea.
Well, there certainly aren't any. Didn't find any patterns in the primes.
That's right. No one knows about any patterns in the primes. Well, I shouldn't say any, but no big patterns in the primes. One thing I want to show you on this is how we could see for this number, and then it's going to show us for a lot of numbers, that this number is not prime lots of times. Okay, so it's going to actually be a fairly simple fact. And what we're going to do is we're going to look at it mod 3. Do you know what mod 3 means?
So it's the remainder. Look at the remainder when you divide by 3.
Yeah.
So it can be 0, 1, or 2.
Right. So what is the remainder when we divide 78,557 by 3?
So if we
I think it's going to be 2.
let's see.
Or yeah.
So if you sum the digits, 32. I think it's 2. Yeah.
Okay. So what number do you know is divisible by 3?
So 78,555.
78,555 is divisible by 3 because the digits are summed to 15 plus 15.
Yeah.
So this is 2 more than a multiple of 3. So if I look at division by 3, 78,557 is the same as what number?
78,551.
Or 2.
So it's the same as what number?
2.
2. It's the same as 2. If all I'm going to do is just divide by 3, this is the same as 2.
Okay.
Okay? So this simplifies a lot. When I'm only for the purposes of dividing by 3, it simplifies to 2 times 2 to the n plus 1. Okay? Now we got to look at powers of 2.
Well, powers of 2, they have some pattern to them, at least their last digit.
We're not going to look at the last digit. We're going to look at multiples of 3.
No, since you have a 2 right here, it's just going to be 2 to the n plus 1.
Yeah, you're right. You're right. We're going to look at powers of 3. You're right. I can simplify this a little bit. 2 to the first power is what mod 3?
It's 2.
2. How about 2 squared mod 3?
1.
How about 2 cubed mod 3?
It is 2.
2.
How about 2 to the 4th?
1.
2 to the 5th?
2.
2.
2 to the
Seems to be a
6th?
pattern.
1.
Oh. See a pattern?
2, 1,
2, 1,
2, 1, 2, 1, 2, 1.
Yeah. Now I've got to multiply this by 2 now, right? Because
Yeah.
that's 2 to the n, so times 2.
Just shifts it down.
Yeah. Or
1, 2, 1, 2, 1,
It's
2.
gonna be 1, 2, 1, 2, 1, 2. What happens when I add 1 to this?
It's
Well, it's gonna go. The ones are gonna become 2s.
Uh-huh.
The 2s are gonna become 0s.
And what does that? What do those zeros mean?
It's divisible by 3.
Yeah. So I just showed that shows us that every even power of 2 for this number is divisible by 3, and therefore
Not prime.
not prime. Okay.
okay.
Does that make sense?
Yeah.
So that shows you at least a little bit of an idea of why this might be a candidate that could work. But just by the argument I put forward, what other numbers might work?
Well, the powers of 2. Well, any power of 2 plus 1.
Well, remember this can only be an odd number.
So any number that is 2 mod 3. Any odd number.
Any odd number that's 2 mod 3. So for example, what's the first one?
5.
5. What's the next one?
8.
Well, it's even.
So 11.
11, yeah. Alright, so let's go up to the computer and see if we can figure out 2 things on the computer.
Okay.
Let's see if we can see a pattern with 5s,
Okay.
like we saw for 3s. And then we'll see if we can see a pattern for why 3 times 2 to the n plus 1 doesn't work. Maybe that's easy. Maybe we can eliminate 3. Okay?
Okay.